All right, we are live. So welcome everyone for joining us for another one of the Siemens webinars. I think we're going to have certainly some exciting material today. I'm just doing a quick audio check to make sure everything sounds okay. Yeah, looks like we're doing good here. Perfect. Okay, so as I mentioned, we are going to have a very interesting topic, kind of expanding off the whole digital twin concept. So we're going to get into that shortly. But for those that are certainly maybe new to this series or don't know me specifically, I wanted to get a chance to at least um, introduce myself. My name is Chris Pollock. I manage our technology application team based here out of New York, so Southern New York. So I have the pleasure of managing a team of certainly advanced specialists, focusing specific on the Cinemeric product portfolio. So I have Dan Struble, that is also a CNC specialist like myself. So we really delve into all things kind of operation and programming based. And then I have two brilliant systems engineers, Brian Baumgardner and Adam Caves, and they really get into more of the back end commissioning, service topics, that kind of stuff. So if we can ever help you guys, feel free to reach out and we can see what we can do. Now, with that being said, just a couple of key points that I love everybody to get a chance to, just start to explore and potentially leverage. Now, what you're going to see over these next two slides, I did include these slides as a PDF in the handouts section of your event. So you can pull them down and you can get direct links to all this stuff. So we do have a series of training classes we host, all Cinemeric based, starting with kind of your entry level, level one, shop floor programming and operation topics. And then we go all the way up to a full advanced level four macro programming. All our courses are 100% complimentary. So if you're looking to increase your skills and knowledge of the Cinemark product portfolio, or you have employees that you want to start to upskill, by all means, take a look at our courses. We also have the Mr. CNC YouTube channel. So we post all of our videos, and this one included will be up on that channel for later viewing. But there's all sorts of additional content there. So if you don't know the channel, I would strongly suggest heading over to it and taking a look at it. Tons of links to other videos that maybe weren't even produced by us. Take a look at the playlist. A lot of information there for you. We also have our virtual product expert program where you can go to our CNC4U website. Again, all these links are in that handout, so make sure you pull that down. And there, if you're interested in learning more about the Siemens product, then what you're going to want to do is you're going to want to go in, you fill out a little page, and then we can set up a one-on-one session with you. They're usually about an hour long, do a Teams meeting, and can kind of dig into all things Siemens and Cinemeric for you. Additionally, we have a content manager. This is a great way of navigating all of the video content we have. So this video as well and this webinar will be included in that content manager on the next release. We try to release them, usually quarterly or so. But pull this down. It's a great way to navigate all of our video contents. We have links to all of our manuals. And don't forget to sign up for our contact list. So if you're not already receiving the emails, the promotional emails, maybe you heard about this event through a colleague, a friend, whoever, get on our contact list so you can continue to get updates as we go. We produce a lot of content. And here are just a couple extra direct links. So as mentioned, all the slides are there for you, can be pulled down. And we have our latest Mr. CNC Insights channel that we've recently stood up, probably about the last year, that is focusing more on commissioning and service topics. So maybe you're a little more interested in the product from that side, from the support side. I would say definitely check out this channel. The two channels are actually linked together. So if you actually look at just below where it says Mr. CNC Insights, a couple lines down, you'll see a direct link to the main channel. So if you just get to the main channel, you can bounce between these two channels. So there is effectively a sister channel of our original. Now, with that being said, I would like to open up and say hello to my guest, Marcel. Marcel, how you doing?
Hey, I'm good. Welcome,
Perfect.
everybody. Pleasure to be here. Thank you for the invitation.
Absolutely. Great to have you here. So, Marcel, we ran into each other, boy, probably maybe a year ago now. It was an OEM's technology event. We just started talking. He did a nice presentation on his product that is, in my mind, kind of the next evolution of the digital twin. And I thought, wow, this would be really cool to show the community, let everybody get a chance to see it. So, just a little bit of background as far as Marcel. He did come from the Fraunhofer. Did I pronounce that right?
Yeah, that's correct.
Close enough.
Yeah.
All right. Institute, where he was focusing on technology consulting projects. And then from there, I'm assuming you kind of took some of that technology as how you stood up this business, right?
Yeah, definitely, exactly. I will also give a short insight about the story, how everything came together a few years ago.
Awesome. So I'm going to hand it over to you, Marcel, to let you
Perfect.
start to drive this. So you
Yeah.
should be sharing now. As we go through, guys, make sure you enter any questions into the question panel. If you put it in the chat, it's okay. I'll find them, but it's best if they're all in the question area. We will do a Q&A session at the end, and if appropriate, maybe we'll throw a few questions at Marcel as we go. But
Yeah, definitely.
with that being said, no further ado, the floor is yours.
Perfect. Yeah. Then thank you again for having the chance to present our technology to hopefully some new people from the US. So from my side, it's a good evening from Germany. Gemineers is based and located in Germany, in Aachen, a city in the west of Germany. And so we are Gemineers. So already in our name, we put the twin, the Gemini, for the twin or delta twin, and the nears to see, you can see it as a pioneers or engineers. And today, yeah, I would like to introduce a little bit so where we come from. What is our goal? What is our technology approach? And for sure, at the end, show you a little live demo of our software. So to start with the topic, I would like to go into the story. So we, or maybe all of you remember, I would say around 10 years back, maybe everything was starting with the data, industry 4.0. Data is the new oil and everything. So everybody was like, yeah, so we can solve every problem now just with data. But in my opinion, I don't know how you see it. Maybe also, Chris, you have an answer to this. So there was, yeah, little disappointment after a few years. So it wasn't the holy grail, I would say. Everything was still complicated. It was hard, especially in the cutting technology, to use the data for a bright approach. So there we saw, okay, it's still, yeah, tough. But still,
Yeah.
we are Fraunhofer Institute, is a research institute. So our professor said to one of my former co-founders, okay, please do some research, what we really can do with data. And this was kind of the start of seeing, okay, 1 second.
Yep, you're good. It's
Yeah,
true too. Like
yeah,
everybody was flooded with data. Nobody knew what to do with it, right?
yeah,
I
definitely.
think they're still challenged sometimes, to be honest.
Yeah, yeah. I would agree. So at the end, the question was, okay, let's see how far can we go with the use of machine data to tackle the questions, to predict part quality, to save time, to optimize the processes at the end, to reduce costs, and to transfer knowledge, to also fight demographic change. Because also here in Germany, I guess it's the same in the US. There's a big challenge with the demographic change of people and especially workers or the workforce on the shop floor. Yeah, so this was the start. And then I would say after a lot of research projects, some funding we have in Germany to help guys like us from a research perspective to really put this technology and put it into a company. So we now look at our companies. So we founded Gemineers 4 years ago as a spin-off of the Fraunhofer Institute. So we now have 32 people working at in our company, mostly software guys, to be honest, to develop the software. We already have more than 30 customers worldwide, so already in the US, in Canada, in Asia, but most of them for sure in Europe. And so I will talk a bit later about the model. So at the end, our software is equipped to one machine tool, and there we sold already more than 50 licenses. So our product is called the Digital Twin Platform. And before I go into this, I think we need to start to talk about what is a digital twin. Because what I see or we see, probably Chris, you agree, is that the digital twin is a really widely used frame for a lot of stuff. So you, at Siemens, you have the digital twin of the NC control, and there are all kind of digital twins out there. When we at Gemineers, when we talk about the digital twin, our core focus is to talk about the digital twin of the workpiece. I will explain later how we get there, but the focus is the digital twin of the workpiece. I just had a pitch earlier today, where I also said, okay, it's a digital twin, and then some guy said, okay, but the digital twin is also CAD model. Yes, somehow, but we want to go further, to have like a most exact virtual representation of a physical object, and this is normally not the CAD model. To make a little bit more clear what we mean, I have an example. We have here an example workpiece, a small blade, and this is what we then call the digital twin. So you directly can see the shape of the real part also in the digital twin, even when you look closer, so that all the deviations are also there. And this is our core concept, to get from machine information to this digital twin and use this on a shop floor and in the manufacturing environment. Why do we think this does matter? So what we see in manufacturing are some basic challenges. We had them a lot of years, so constantly growing product and process complexity, more and more fragmented and heterogeneous manufacturing environments, and for sure, like every time you can say this, I would say increasing market competition. And after all this industrialization, automation, and everything, we now see the digitalization and also the digital twin as one big part of it, as an opportunity to use the manufacturing data, create visibility, learn from the past about your current processes, know what is happening, so know the present, and at the end, predict the future, to also gain a new level of the competitive edge. That said, I want to give some more background on where we are coming from, or what is our core focus. So we have a software product, so the digital twin. So we have two factory installation partners with Jim and Grob. So this means you can there buy the software directly from the machine tool provider, but most of the time we do a retrofit, because we see that a lot of companies, they don't have just one machine tool provider, they have several. So they have, you know them all. So this is also one part of this heterogeneous fragmented shop floors. We also have our research partners. So this is our history, and also still at the present and the future, to be ahead of a lot of developments. We also collaborate in research projects. As there are we have here some references of our customers. So from a lot of different industries, from medical industry, aerospace industry, energy industry, tool and die making. So at the end, our product is tailored to everybody who is doing at the end CNC machining. Before I go into the detail or open the curtain how the magic is happening, I would like to start to ask yourself, or maybe I can ask you, Chris. So
Sure.
normally when you have such a part, like we have here the blade, how would you measure it? How do you ensure the quality so it's in shape?
Certainly a challenging process. Obviously, we could leverage an external CMM process.
Yeah.
That could be one method.
Yeah.
We have looked at some other like on-machine probing solutions. I
Yeah.
would say on a blade like this, that would be very challenging.
Definitely. Yeah.
Certainly more prismatic parts, that's a little bit easier of a solution.
Yeah. I agree. So also another option, but also complicated for the 3D free-form surface is to have like an optical measurement with the GOM system or something like this.
Yep.
But everything has its own, I would say, challenges and advantages. So now what we are thinking of, because we create this digital twin. So just imagine you have this digital twin. We now are able to say, okay, let's compare the digital twin to the nominal geometry. You directly have a quality evaluation. And this was also our core idea when we start this project to see, okay, how can we predict the quality?
And you'll get enough fidelity out of the model?
Yeah, definitely. Depending a little bit on some requirements like the machine tool, the frequency, and everything. But I can explain this a little bit, the requirements and the boundaries maybe later on in the software.
Cool.
So getting back to how it does work. So how can we get to this digital twin? So first, we need to get the data. So we usually equip an IPC, industrial PC, directly to the NC control and get out their high frequency data so that when during the part is manufactured, we already can see some data and we get data like positions, orientations, drive loads, temperatures, and if possible, additional sensors. So there we don't need to put any new sensors into the machine. So we just use what is already there because we are connecting directly to the NC control. So we started everything with the Siemens numeric 840D solution line. And also we added Heidenhain and Fano controllers lately. So this is really important that we get a high frequency data and directly from the NC control. But there, the advantage is so that we can, at the end, equip any machine tool with those NC controls. And then what we do is with this data, so I just showed the data connector. Then our USP comes in. So this is what we call the technology core. Because just using data and displaying it is just one thing. So this is, I would say it's not easy, but it's the easier thing. But then to get from this data to a digital twin, which really represents what is currently on the machine and the part looks like, we have to start to see, okay, what are the effects, why the part doesn't look like this. And when we did all this testing, we saw, okay, one of the biggest effects for this blade manufacturing, but also for a lot of different parts is tool deflection caused by a higher cutting force. And there we created algorithm to go from the machine data to calculating a cutting force, to calculating tool deflection, and also taking into account tool wear. So what we do based on this data in close real time, so we do it like batching for each smaller process step, and then we create a digital twin of each of those processes, and then it's available in what we call the data hub. So at the end, I will also show this in the next in an example. So our completely software is browser-based, because we want that a lot of people in the company on the shop floor in the quality department, they have access to this data, so that we also can produce like a new single source of truth. Here's an example how it does work. So you see also, so in the spindle load is here displayed, and using this information, we can also calculate tool deflection. We look into tool wear and also the real tool pass. So what the post processor did at the end with this part, and then we create this digital twin, compare it to the nominal, and then we have this nice color map here. And this is everything is done automatically. So you just need to put in the geometries, the raw part, finish part, and the tool information, connect the machine, and then you're good to go. And this does work for a lot of different kind of applications or different kind of parts. So smaller aluminum parts like the jet bracket here, or really big parts like this chain wheel or this pintle plate, the blisk. So at the end, everything started a little bit with the blisk manufacturing. So also when you visit our website, you see a lot of this blisk and this manufacturing, but also for example, for the tool and die industry. Because what's also the real benefit is that this is not any kind of machine learning or AI. So this is physics. So there it's already is working with the very first part. So this is why, for example, tool and die shops, they also use our software. And at the end, this digital twin is just one application, right? How you can use the data. So this was the starting point, and also, to be honest, this is the one of the highest level of the data usage. So you have different other possibilities you can use the data for. For example, you have a lot of insights in the real feed rate, in the forces, everything. So you can use it to be much more faster in the ramp up and to optimize your processes. You also have the possibility, based on this 24/7 monitoring, that you can see really easily what's your OEE status, and also can put into this idea not just the machine is on, machine is running, but also machine is engaged in everything. When we talk about the digital twin, so as I said at the beginning, okay, we focus on the digital twin of the part. But thinking, when we do this digital twin creation, so there we use like a material removal simulation, we also know the complete engagement of the tool. So we also can create the digital twin of the cutting tool and have a complete cutting tool traceability. Same goes for the machine tool. So there's something that's currently under development. So when you also think about, okay, well, when we have all this monitoring of the data, we can also think about predictive maintenance needs, just based on the data. And also something which is, I think, quite interesting for the serious production is when we talk about statistical process control or process monitoring in general. So to see, okay, how can I use the data to supervise my process on the shop floor with, just with data. And this is, maybe just the start. I want like to focus a little bit more on the software, and I change to it. Give me a second.
No worries. Always cool to get a nice live demo of it.
Definitely. So
we really see its power.
Yeah, have to put it a little bit better here. Does it work? Yeah. So this is good. So like I said, everything is web browser based. So at the end, it's still not in the cloud. So it's on the server. So this is a demo for such purposes. And everything in our software is app based. It's a little bit like an app. So currently we have 5 different apps. So we have the Twin Creator, where you put in everything which is necessary, like the raw part, the finished part geometry. you can connect the machine tool, and you can set up the tools. Then the Twin Explorer, where most of the data is currently to inspect everything. The machine viewer is also something I will show later, is a live viewer where you can follow what is currently happening on your machine tool. Tool tracer is the more information about the tool and the tool usage, and the efficiency monitor is this OEE tracking. So starting at, I think I just put one. Wait a second, I need to make it smaller again. Yeah, so I already prepared a little bit to save us the loading times over the internet. A little bit what we do. So when we go to the live demo, so this is currently the live one. So you see in an overview window, you can follow each of your machines. So I think there's also other software out there which can do this. But we also have here the information. So currently we as a startup, so we don't produce parts or something. So this is why we don't have our own machine. So this is why we use a Siemens Run My Virtual Machine to do some testing for our software. So this is what you can see here right now. And here on the side, we have what we call a fake machine. It's a demo machine where we just run 24/7 the same process to give you some demo. What we also can see here is which tool is currently on the machine and for how long. So this is quite good runtime, I would say, for a tool, and also which part is currently on the machine. When you now click on the machine, you also have some information about some information from the HMI, like also tool again, feed rate override, and also spindle speed. And when you now go to the visualizer, so this is what I already loaded in here, you can even follow the tool on the tool path to see cool. What is currently doing. So here was the tool change. Now it's getting back. And now we can follow again here the real tool path. And this is something you could do, for example, from anywhere in the world. So the machine could be, I don't know, in the US, maybe, Chris, we equip your machine in the back, and I can follow it up from here because we have the data connected, and then we can see everything.
Yeah, cool.
Currently we see the spindle load. We can also change maybe to the axis load and feed rates. So this is just some basic stuff we use, so it's you can follow it up. But the real magic is happening in the Twin Explorer then. So when we go here in this Twin Explorer, you have an overview about all of your products. So we just saw this Blisk. So then we have this plate I showed in the presentation, some other demo material. Just imagine you have all your parts here. So you just need to set them up once, and then every part you're doing is getting into this serial number here. Everything is automatic. You just need to put some UGOT information, for example, into your program so that we can align the data with the serial number. And in this overview, you directly can see, okay, some basic information. So throughput time, cycle time, start, end time. And then what is new, what we bring to the party is the performance and the quality. So the quality is something directly when we talk about the digital twin. So here we directly compare our digital twin with the nominal. If everything is good in tolerance, it's green. If there's some area which is not in tolerance, we directly go to this non-conformity. Next thing you can see is this performance. So this is what we call is the add to cut ratio. Because what we see, especially when there's a lot of pressure on the CAM program, so there are a lot of programs out there which are running a lot in air. So there's not too much engagement. And this KPI directly tell you, okay, how much engagement do we have in your process? Yeah. So for sure, there are a lot of processes where it's necessary and you don't have the best KPI of engagement, but this gives you a start to look into processes you may can optimize and at the end save time and money. When we now click on this, so the rest is the process and automation, we go to the visualizer, which I already opened here and load all the part geometries. There we can really go and have a deep dive into this information. So everything is starting with the raw part. So here it's an STL, just put it into the software, and the finished part. So this is how the part should look like. Then what our software is doing when it's connected to the machine, we directly or 24/7 at the end acquire all the machine data. So from each process step. So this was, for example, the first the measurement. You can see it like this.
Yeah.
And then we went to the first roughing process. So here you can see now in the coloring the values of the data we collected. So when we maybe look a little bit closer here. So red doesn't mean bad or something like this. It's just here in this 4,500. When I would pick it up, I don't know, to 7,000, you would see, okay, we can change the color. Here, the idea is to see, okay, what is happening on my machine? Now, because the program feed rate is 4,500. But we can see here a lot of deceleration and acceleration process. And a lot of time, so you're not able to see this. You're also, from time to time, not able to really simulate it. So there's simulation software out there that can it pretty good, I would say. But still, from time to time, the processor is doing something which you're not able to maybe control or you can see directly. Besides this information, so we have a lot of different stuff. So the position and offsets, but we already see it in 3D along the toolpath. Feed rate override, spindle speed override, relative timestamp to see where did the process start, where did it end it, when it's a little bit more complex. And then, which is really interesting for us, are the loads. So all the loads of all axes, and also, for example, the spindle load. Here we can see, okay, in the middle also where we have a higher engagement, so there we also have a higher spindle load. So this is also just getting data from the machine and visualize it. Now the technology core comes in place. So now we use, or we do like a material removal simulation on this real data to calculate engagement parameters like chip contact area, depth of cut, width of cut, removal rate, and so on, to see, okay, what is happening. So this is why we need also the raw part material and the information about the tool geometry. And this is done in parallel. So when the process is ready, also the digital twin is ready. So then you directly can see it here. Based also on this engagement parameters, we then calculate technology parameters like the cutting force and also the tool deflection, and take this into account when we create this digital twin. So here we also can see, okay, how big was the tool deflection along the tool path. A lot of time, the reason because something is off, because maybe some more tool wear. So this is why we have more tool deflection, difference in the material, and so on. Here we can make it visible. And based on this, we also create a digital twin after each process step. So when this process is ready, we already have a digital twin. Look at this part here. So it's the status of this workpiece after roughing. And this is what we then call the digital twin, because we can visualize the current state of the part after each process and at the end of at any time. Here, this also gives you the ability to look in between, okay, what is currently happening here on the process. When we now say, okay, I have this digital twin, I know the finish part geometry. Now it's an easy thing to say, okay, compare these two geometries and see how big is the difference. And there we see, okay, everything is red when we look into the scale from 0.1 millimeter. But when we now go to maybe 2 millimeter, there we can see how much material is left in which area. So especially when you think about the process chain, you can also use it after pre-finishing maybe to see, do I have a smooth surface to go into the finishing process? And at the end, like I said, we do this for all of the processes here. Then we have the last digital twin. Now everything green because I still have the scale. But when I go deeper in maybe 0.06 plus minus, there we directly can see, oh, I have a problem. This is what you can see here. Now, when you also want to identify, okay, how big is the problem? So one of our newest feature is to also put in some measuring points to say, okay, I want to know here the deviation. Okay, here's on 0. So there's minus 0.056. Here I have too much material left. So I can really see, like in a GOM system, I would say, or optical measurement system, it doesn't matter which one, you can put some points on it, and also you can predefine them when you have like a series production, and then check if everything is good on this specific point. What you also can do, just going to remove them. And you're looking into the process, because normally what you have when you do data collection and data analysis, you don't have this 3D visualization. You already have the benefit to look more into here. But what we also have is like a 2D visualization. So we also can see, okay, when we have some, I don't know, maybe let's go into the spindle load. So not the, where's the filtered one? Or we go into the stool deflection. We see in this process here where it's higher, and we can click on the process. Need to be quite small. I think this was the this was the wrong problem, the wrong process. And here also we have the spindle load. This looks more like a spindle load.
Yep.
Yeah, I selected the measurement. So it would be really bad when there would be a really high spindle load on the measurement on the touch probe. Here you can see it over time. And now when you also go back in there, you can select the point on here, and then you can directly see it where it is in here. So you also have this coloration. When you want like to identify peaks and everything, you can directly switch in it. And also, this is just the beginning of our usability. So there's also more up in the future. Now we see, the digital twin, there's something off. So there we have a problem. So now what? Any idea what happened, Chris?
So I'm hoping that we can set up some kind of a trigger to be able to notify me if we start going outside of some nominal tolerance band.
So this alert system is also in development for, I would say, the beginning or the mid of next year. This is definitely the next thing. Currently, we have more like the pull. So now when we have the situation, so we see the digital twin is red, but now we would like to understand why is it out of tolerance. And this is also one really important use case of this data we saw then when we had it roll out to the customers. So now we can start to investigate what happened. So here we saw on this side, okay, there's something off, but here I don't have a lot of tool deflection. Also, when I go maybe to the spindle load, okay, doesn't look that bad. And also the feed rate, it has some acceleration and deceleration, but still maybe not the biggest cause. What we also have is the toolpath orientation deviation and position deviation. So when we now go here, we see, okay, in this area, there was a really big difference. So when an orientation deviation of more than 2%. So to get the rabbit out of the box, I don't know if it's also in the US like something you say to unveil the magic, is what we did here, because we wanted to create this deviation. We played around with the cycle H32 and made the toolpath tolerance a lot bigger. So the machine moved a lot faster over the corner, causing and tolerating this toolpath orientation deviation, which it normally wouldn't do. And here we have the data. So this does mean, so when you have a problem, or not just something for the optimization, but also when you have a problem and you have the monitoring of the data 24/7, it's much easier and faster to do troubleshooting because you have the full transparency. So when you normally have, I don't know, 8, 9, 10 different reasons why the part is wrong or something is wrong, you can directly see in a few clicks, okay, it wasn't this, it wasn't that, maybe it is this, can directly identify it and use this information to be faster in the troubleshooting and faster back on production.
So let me ask you this. So how many of your customers, obviously we're talking about real-time data while the machine's running, while it's cutting. How many of your customers are starting to leverage this upstream, maybe up in programming off of our digital twin, kind of like you're doing here now, to anticipate some of these problems even before they get down on the floor?
Yeah. Currently, this is definitely the right question. We're also thinking about this, and this is also the question by the customer. So what is the current process? So now we have the what was happening. So now the know what. So the question. Now currently, so now the programmer knows, okay, where to look at, how to optimize the program. I can also imagine in the future so that we also put it together with the CAMP software to do this feedback loop. But there's still a lot of stuff and challenges to do until we get there.
Sure.
Yeah. What our customer doing is, so they use like our software to do and to analyze the program with air cuts, or to connect it to a run my virtual machine as well. And to also see, okay, how does the program behave when we look into it with our gemineers software. It makes sense when you have high material costs like Inconel, titanium. Before you waste, I don't know, 20,000 US dollar on material, I think you have the time to run the the machine without a part on it.
Yeah, absolutely, for sure. And obviously, the one thing we won't be able to predict is the spindle load piece, but outside of that, yeah, it would still give you quite a bit of insight. Interesting.
Definitely. So also, I think when you talk to customers, also people from the industry, they are thinking out, okay, but maybe we can then predict based on all the data, the spindle load of the future, and so on. So I think our list of things we want to develop in the future is really long, and also the demand. So we are currently still in the start, and on the level of this transparency and giving access to something which is already there, but normally you're not using it. So this is currently the idea, and also the usage. Yeah. So far for the Twin Explorer, let me think if I missed anything. No, which is also a nice gadget. Here you have like a share button. Also, from your smartphone, you can directly share this and send it maybe to your programmer when you're on the machine, or to somebody else, to directly have new single source of truth, to talk about something. A lot of customers, they say, for example, okay, maybe during the night shift, yeah, something happened, it sounds weird, but I don't know.
Right.
You know. Yeah. All right. Going from this, we also have the the machine fair we already showed, the tool tracer. So here we have the information about the tool. I have to check here. So it's also, it's like a beta phase right now here about this tool. And here we see for each data point, it's one process. So here you can check, okay, when was the process, what was the process duration, also then in the next step, the removed volume. So because when we look into at the cutting tool, we don't want to just look into tool in spindle, because we saw this engagement parameters. So this is just half of the truth. We want to look into how much time the tool was in material, and then also which area of the tool was in material. So when we check here, we also have information about the tool, height of the tool, how much the tool was in contact with which part of the cutting edge for how long. This also give us the opportunity to look more into how I can save at the end tool money on tools, and also how can I extend the tool life. And I think this would be also one of the next questions. Can we trigger a sister tool change just based on the tool data? Not yet. Also, is the next one of the next steps to say, okay, use this instead of your 200 minutes in material, because you know this is the safe number. Here you use, okay, use it until a specific limit, and then change it, because sometimes still your experience is not good because, I don't know, there was more material on your cast iron or something like this, and you hit a cutting edge badly. So yeah, still a lot of stuff to do. Last part would be the efficiency monitor. Here we also see the machines and also basic stuff. So here, so we don't use our Run My Virtual Machine so much lately, but the demo is running, a lot of time. And now we can also have like basic information like you have with also different other systems. So it's just an add-on. Customer ask us, okay, can we also have some OEE, because you have the data, right? So then we said, okay, for sure we can do it. And the next thing is also to add the quality aspect to it, so that we just don't, not only know, okay, the machine is running, the machine is, or the machine is on, the machine is running. Next thing would be, is the machine really cutting or in contact? And is the machine producing good parts? To bring also much more insight into this. So overall, where I see us, is that we are also a new piece of puzzle to all this manufacturing environment. So we have this USP, especially for the cutting industry. So to bring our cutting manufacturing knowledge into the software and provide it to a wide range at the end of companies, customers, and manufacturing environments. So
very cool.
Yeah,
very, very cool.
Yeah, this is also something. I would sum up a little bit. I would say the pitch, the presentation. So when we talk about the digital twin, it's the digital twin of the workpiece. We use real-time machine data collected 24/7 to have a full traceability, to create a digital twin based on the on this machine data, use it for different kind of applications, starting with predicting or evaluation quad quality, doing troubleshooting, optimize processes, and have a few or a high transparency on your complete shop floor. Yeah, and this would be, I would say, more or less the end. Or let me put this back here. Wrong rate. So.
Perfect. Well, that was a great presentation, Marcel, and we've got a lot of questions to dig through. The audience was
That's
certainly
really good.
kind of busy, so that's
Yeah.
so good. Here, maybe I'll switch to our panel view so everybody get a chance to see us. I left it concentrating on the slide deck at that point because that's
No
certainly
problem.
the most interesting. All right, let's dig into them a little bit. So first, we use Vericut or CG Tech's Vericut simulator. How can this technology help us since we already have the CAD models versus program comparison before we manufacture a part, face, toolware, and optimization features that come with that software package?
Yeah, that's a really good question also. So, like I said, Vericut is a simulation program. I think it's really good. It's also widely known, used also here in Europe, Germany, everywhere, and doing the simulation and prediction of what is happening. Also with their force module, so they have a start to predict these forces. But still, what we see, there's still something happening which you're not able to predict on the machine. So in regard on toolware, material, how should I say it, properties, and still, yeah, it's not completely the reality. So what we want to do is to give you still, especially when you have really complex geometries, like Bliskin aerospace, or some nasty materials like Inconel, titanium, hardened steel. So it's hard to predict what is happening, and this is where we come in. So to give you this traceability, and to learn from it, and to optimize it. So I would say the process chain would be do the programming, use maybe Vericut or different simulation software, also, and then go to the machine. And when you do the first cuts, then do it with gemineers and learn from it, and also optimize and shorten the feedback loops. This is
And also get that fingerprint, right, from part to
yeah,
part to part, right, which is critical, especially if we're doing larger batch runs,
definitely.
which somebody like a Vericut or even our product, our digital twin, my virtual
Yeah,
machine, it's great upstream, but it's not
yeah,
going to give us that live real-time data from piece to piece for sure.
exactly.
All right. So for aluminum aerospace parts, does this show distortion after the parts are released? So free state distortion conditions after machining.
Yeah. Not directly, to be honest. No, for sure, this is something which is hard to predict just based on the machine data. So we already have experience with, so it's possible to do like an FEM simulation of the part before, to see when, how does it deform during the process. But this relief, it's
Yeah.
not able to see, to be honest. So we do a lot of magic, but we're not able to do everything. So maybe there's something in the future. We know the problem, or we also say, okay, then also when you have like really, really thin-walled parts, you have to put it in there somehow, or to see, okay, how much real of your tolerance or your problem is this part deflection.
Yeah. Yeah, I could see it'd be very difficult to anticipate the stresses that are
No,
being implemented on the part during
yeah,
machining and effectively can change from material batch to material batch. I mean, different
definitely.
anomalies within it, but great
Yeah,
question for sure. And
yeah,
I'm sure that's kind of like the holy grail that we all want to kind of get to for
yeah.
sure. How accurate is the digital twin model compared to a CMM measurement?
That's also always a good question. And because we know this question, I also have like a slide for it. Yeah, so for sure, this data is it's a quality evaluation, and we also did a lot of testing versus CMM versus optical measurement and also the touch probe. Here we have an example of a comparison also of Blisk, where we see, okay, the profile deviation of such a of a profile cut, and in blue we see the CMM, and in red, purple, not red, something reddish, is the CMM. Overall, here we had a standard deviation between both measurements of 9 microns, so it was quite accurate.
Yeah.
And what we see when we look into the digital twin of this blade, even though the critical areas here between profile cut 4 and 5, you're not able to see with the CMM. But this is something which is still depending on, so I wouldn't say that we can directly guarantee this amount of accuracy for all operations, because it's depending how much signal do you have or sensitivity between the tool and the part. So what can you measure, which is happening in the process? Just imagine, so you have, I don't know, a HSK 100 spindle with, I don't know, 250 Newton meters. You use a 1 millimeter tool with a really high spindle speed, so there's
effectively no load.
There's really hard to see something. So there's like a sweet spot. It's different from application to application, but overall, when we compare it, so we have a quite high overload. So the average feedback from our customer is a quality of around plus minus 10 microns to other measurement systems, because what we also see, so you have different advantages and disadvantages for each measurement tool. So like measuring time, so there we are really fast because it's on the fly. Also programming time, it's just the setup of the part, and also the time until the result is available. And also for sure for the costs and number of measured points. There's advantage for sure. It's still on the machine, so we still have the effect of the machine. So it's always something about the pros and cons when you do this on the fly evaluation on the machine.
Cool. All right. Let's keep going through here.
Yep.
All right. Where was I? How about to add additional data such as noise or vibration during the cutting process?
Yeah, we can do this. I think I have one example here. We check. So we can add additional sensors to the software. And then I think in this one we had also, for example, the spindle acceleration. So there are some machine tool providers, they already have them as a standard in the machine tool. But you also can just put like an additional sensor in it. So when we connect the data,
like a accelerometer, something along those lines.
Yeah, we can add it, and also it helps to give more insight to the process. As closer you're getting to the real process, the better at the end.
Yeah, absolutely. How about the use of report information to guide the CMM inspection afterwards?
Yeah, also I think a really good approach. Also, we are working on that currently. I'm in, I would say, currently in discussion with the customer how we can do this. Just imagine you have like a series production. Maybe you have one big setup box, I would say, on the machine. You have 20 parts on it, and then what to do. So the idea is to say, okay, we can decide based on our quality. Okay, please have a look into these 4 parts because they show the most deviation to the nominal, or they have like in the process the most deviation to the nominal process value. And this is something different. It's nothing out of the box right now, to be honest, but at the end, the data gives you the ability to do so. We'll also say, okay, we're not able to get rid of any measurement equipment in the shop floor.
Sure.
So it's a start. Just imagine, okay, you have like a series production. Normally, right now, you measure every 10th part. 10 parts, measure. 10 parts, measure. Now you can say, without any additional measurement equipment, you measure every part and maybe just put every 50 parts or 100 parts on the CMM. So I think this is the approach we are going here with this technology.
Yeah, it makes perfect sense.
Yeah.
We also got another question came in. Can you show an example of a SPC?
No, so it's currently in development, unfortunately. So this to have it like this, because it's quite tricky. Because we also see there's multiple ways, or also some stuff out there to do like process monitoring, but somehow we want to integrate the digital twin thinking into it. So this is why we currently, it's taking longer than we want. It's also, honestly, it's software, but we want to make it as perfect as possible. So this is why I'm not able to show an example for this right now.
Got it. No worries.
Yeah.
So how difficult would it be to install it on a non-DMG or Grove machine? Obviously, you mentioned you're partnering with those two.
Yeah. It's no problem. So the basic, so we just need one piece of hardware. It could be, so there are two ways, either a bigger IPC for the data acquisition, data analysis and data visualization. So then you have a bigger Siemens IPC, we also use a lot of time. Or you use the smaller one just for the data acquisition and then do the rest on an internal server. And then you can directly go. So the fastest time we connected the Ethernet cable to the switch in the machine and had the data was, I think, 2 or 3 minutes.
That's pretty
Sometimes
good.
it takes a little bit longer,
Yeah.
but to be honest, it's, I think, normally average is 2 hours maybe.
Got it.
Yeah.
Another question came in. Does this conform to aerospace customer requirements for CMM part data? So proof of conformance.
Yeah. No, it doesn't. So like you can imagine, we won't get rid of the overall CMM measurements in the aerospace industry anytime soon because the process behind it is huge.
Yeah.
So, but what is currently ongoing? So here in Germany, we have this big, I would say, a program. It's public funded. It's called Manufacturing X. It's Container X. So there's a lot of different in there. I think also Siemens takes a lot a part in it in the different places. So there's Factory X, and also there's Aerospace X, where we also part of it. So it's also together with Airbus and I think SAP and some other bigger companies, where we now create or discuss, okay, how can we manage or to use this data in the future also between different stakeholders to optimize the complete value chain in manufacturing.
Well, that was a great presentation, as I mentioned. Ton of great engagement from the audience. Certainly, thanks everybody for joining us. Marcel, thank you for certainly spending the time and getting a chance to talk to the audience and hang out here a little bit. And I'd love to, maybe let's take it to a next step. Maybe we'll get a chance to do hook it up to one of the machines and play with it a little bit. I think it's
for sure.
very
Would be really nice. Thank you for having me.
Oh, absolutely. Our pleasure. Anytime. And again, thanks everybody. I know we're a few minutes over the hour, so we'll might as well wrap things up. But for those of us in the U.S., have a happy Thanksgiving. That's yep. We have Thanksgiving coming up next week, so by all means, take a little time off, eat a little turkey, take a nice nap. That's what I'm going to do, and we'll talk to everybody real soon. All right. So thanks, Marcel. Thanks, everybody. And we look forward to seeing you next time. Have a great
day. Bye, guys.
Bye-bye.
Happy Thanksgiving.